Hey everyone, today we're going to start with 3.1, which is Introduction to Rational Functions. So let's define what a rational function is. It is a function that the ratio of polynomial functions. So we have our numerator and our denominator, P and Q, and both are polynomial functions. And we did that last time, remember? So when we look at this to determine if this is a rational function or not, we just have to look at our numerator and our denominator. Is our numerator a polynomial? Yes, it is. Because remember, a polynomial means that the exponents have to be a positive integer. Okay, no decimals, no fractions, no negatives, and no x's. And then let's look at our denominator. Yes, that works too. So yes, this is a rational function. Okay, because again, I'm going to highlight this, P and Q are both polynomial functions. Okay, now let's look at B here, or g of x. If we look at our numerator here, what does the square root of x actually stand for? Well, the square root of x is actually x to the 1/2. So as you can see, that our numerator is not a polynomial. So g of x is not a rational function. Sorry guys, I'm writing slow. There we go. All right, so next, domains. Domains of rational functions. So recall that a function is defined only if the denominator is not 0, right? That can't happen. So when we find the domain of a rational function, what we're looking at is that denominator. What we're saying is that x squared minus 9, in this case, cannot equal 0. So when I solve for this, I get x squared equals 9. And then x equals, and be careful of this because when you take the square root, you get plus or minus 3. And don't forget, this is not equal to. This counts, guys. Make sure you say does not equal to. Then we're going to actually write it in interval notation. So of course, then we start with negative infinity. We go to the first one that it can't be. And then start back at that. Go to the second one, it can't be. Start back at that and go to infinity. Okay, so this does not include negative 3 and 3 because we have parentheses there. Okay, now let's look at B, which is g of x. Again, I'm going to take x squared plus 9, which is in the denominator, set it not equal to 0 because that's what we don't want it to be. But as I solve for this, we get x squared can't equal negative 9. Well, a squared number will never equal a negative number, right? It always equals a positive. So this would be no values, right? Because this can't happen. So since we don't have an issue here, our domain is automatically negative infinity to infinity. And in the next one here, it is the same as A. Now, many of you might remember from secondary 3 or some of you from calculus that you might be able to cross off. But right now, when we are doing domain, you do not want to simplify. So don't simplify before domain. If you simplify before domain, you're gonna you might miss value because of a hole, and we'll explain that later, okay? So this turns out to be the same as A. Okay, same thing. All right, next at the bottom here, this reminds us of how to find X and Y intercepts. So let me get my highlighter so we can highlight some good things. For any function, an x-intercept occurs at the value of x, which the output function equals 0. So the x-intercept is where the output value is 0. For rational functions, the output function is 0 only when the numerator. So the idea is to find the x-intercepts, guys, we set the numerator to 0 and solve. And we have to keep in mind that the x-intercept must be in the domain of the rational function. If it's not in the domain, it's probably a hole and it's not included, okay? The y-intercept's so much easier, right? Because the y-intercept happens when x equals 0. So all you have to do is plug in. If the function is not defined at 0, then there is no y-intercept. We'll get into that as we go along. All right, my printer printed these out back and forth, or on each page, so sorry. Okay, so example 3 here. What we are going to do is we are going to find the x and y intercepts for these rational functions. So let me get my pencil. Okay, so remember, to find the x-intercept, remember what we said? We set the numerator equal to 0. So x equals -1. Now, I want to tell you guys this. The idea is that an x and y intercept is a coordinate pair. So when you write down your answer, it has to be a number, comma, another number. Okay, if you left it like this, this is not a coordinate. This is actually a line. Okay, so we have to rewrite this as -1, 0. And -1 is in our domain. Remember, these are the same functions. Well, these two are the same functions as on the other page. So remember in F here, and in this new G, because it's the same thing, we're not including -3 and 3. So we'll just be careful of that. The y-intercept is when we put in 0 for x. So when we get that, we get 1/9. So our y-intercept is 0, 1/9. And we're done. Let's do it on the next one here. Okay, x-intercept. Let's remember that, by the way, x squared plus k, like on the other side, has no restrictions. We're all good. So I take my numerator, set it equal to 0, and solve. So our intercept is -3, 0. Our y-intercept, we have to plug in 0, so 0 plus 3 all over 0 squared plus 9, and we get 1/3. So we've got 0, 1/3. All right, let's talk C here. Okay, C, x-intercept. Set our numerator equal to 0. Wait a second. That can't happen. That doesn't work. So since it doesn't work and there's nothing else for us to do, that means we have no x-intercept. Don't put 0, guys, because 0 is an actual number. So no x-intercept. Y-intercept, right? negative 2 all over 0 squared minus 9. So we get, don't forget, it's a negative over negative, which is a positive, so 2/9. So we get 0, comma, 2/9. Done. All right, identifying vertical asymptotes. So consider the function 2x minus 1 over x plus 1. Notice that x cannot equal negative 1, right? Because we can't have that in the denominator. If we look at the graph, we see that there is a vertical asymptote at x equals negative 1. So in our domain, x cannot equal 1. So what do we set that as? We set that as a vertical asymptote. What does that mean? It means our graph will get really, really close, but never touch. Okay. So the line x equals c is called the vertical asymptote of the graph of y equals f of x. So we have to the left side and to the right side. Okay, so as we're approaching. So in this case, our left side is going up to infinity. Our right side is going down to negative infinity. Okay. All right. So how do we find this without seeing the graph? Because we don't have a graphing calculator, right? Well, first of all, we want to reduce the fraction as much as possible. Okay, so numerator, denominator. If anything crosses off, cross it off. Then we set the new denominator equal to 0. Whatever we come out with, that would be our vertical asymptote. Okay, so these are the strategies that we will use. Okay, next paper. Let's do some practice with this. Let's identify those vertical asymptotes. Okay. So first we're going to simplify as much as we can. So in this case, we might factor first to be able to see if we can simplify anything. So we get x plus 1 all over, and this is, sorry, something to drink. This is the difference of 2 squares, so that gives us x plus 3 times x minus 3. Now guys, can anything cancel out? No. So that means we're going to set our denominator equal to 0. That means in this case that each part equals 0. So that means we have an x-intercept at x equals negative, x-intercept, a vertical asymptote at negative 3, and at x equals 3. And the great thing is, because a vertical asymptote is a line, these are our answers. So I'm just going to label this for us so we have this in our notes. So the vertical asymptotes, there's 2 of them in this case. All right, let's talk about here. So, we're going to simplify as much as can be. Wait, we can't simplify that because it's addition there. It's not a difference. It's an addition, so that doesn't work. So what we do again is we set our denominator equal to 0, but we run into the same idea that we get x squared equals negative 9. This can never happen, so no vertical asymptotes. Okay. The other way I usually say this, guys, is once you simplify, if you can at all, you ask yourself, are there any problems still in the denominator? And in this case, no, this is not a problem. This will never be 0, so no vertical asymptotes. All right, see, you knew we were going to do one where we could actually simplify. So we have x plus 3, and then the denominator here, we have a difference of squares, so x plus 3 times x minus 3. I'm going to show you guys something because this is one of the biggest mistakes people make. Yes, we can cross off this x minus 3. That is awesome. But what is left? In the numerator, what's left is 1. In the denominator, we're left with x minus 3. Many students bring that up and you can't do that. It belongs in the denominator. Now we set our denominator equal to 0. And we know that there is a vertical asymptote at 3. Now, of course, do you have to do all these algebraic steps? No, if you know of a faster way or you can see it, because we've done so many of these throughout the years, go for it. I'm just showing you where we get it from. Okay, so those were vertical asymptotes. Now we're going to start talking about horizontal asymptotes. So let's take another look at the function 2x minus 1 all over x plus 1. Notice it seems to level out as we move left and right. So as we move to the left, as you can see, it's getting closer and closer to 2. And as we move to the right, it gets closer and closer to 2. That is a horizontal asymptote, okay? It always happens at the end. So, in other words, as x goes to negative infinity and as x goes to infinity, okay? Horizontal asymptotes for a rational function occurs when the degree of the numerator is less than or equal to the denominator. So I'm going to highlight that. So horizontal asymptotes of rational functions occur when the degree of the numerator is less than or equal to the degree of the denominator. If the degree of the numerator is greater than the degree of the denominator, the graph will not have a horizontal asymptote. Okay, but we're going to talk about that more later. Okay, so how do we identify horizontal asymptotes? Okay, remember there's two. When the degree is less than, the numerator is less than the denominator, or when they are the same. Okay, so when the degree of the numerator is less than the degree of the denominator, then the horizontal asymptote will always be y equals 0. When the degrees are the same, the horizontal asymptote will be the leading coefficients, okay? So keep that in mind as we do these examples. Okay, sorry, I'm trying to get my notes, guys. Right there. Okay. All right. So let's go up about A here. Okay. Now remember, we're looking at the leading term. The leading term has the highest exponent. So right now I'm looking at 5x and x squared. In this case, our P is less than Q. So that means there's automatically a horizontal asymptote at y equals 0. Now remember, it's horizontal. Horizontal line is y equals, vertical, hence vertical asymptotes, are x equals. Okay, let's look at this one. We have x squared and x. In this case, P is greater than Q. So this means no horizontal asymptote. And it's actually a oblique one or slanted, okay? So I'm going to just note this for now, but we will talk about these in 3.3. Okay, oblique. Okay, so what do we do with that? Okay, next we have less than, we have greater than, and of course now we're going to have equal. Again, leading term is the highest degree. So I have a 6x cubed and a negative 2x cubed. What some people might do is actually rearrange this to be in standard form. And then you'll see that it's at negative 2. Okay, so since P equals Q, then we use the coefficients in front. As you can see in the numerator, we have 6. In the denominator, we have negative 2. Well, of course, let's reduce that. That gives us negative 3. So, of course, don't forget to put the y equals, and that's a horizontal asymptote. Okay? Graphing. Now that we have all these parts, we should be able to do some sketching, okay? Now I'm going to say sketch because we need to figure out, hey, is our question going to make us do exact, so we have to have specific points, or can we just sketch out what it looks like? So there are a couple of things we have to go through when we're going to graph. You want to find the domain, find the restrictions, anything like that. Then we're going to reduce the rational function into the smallest terms possible. We'll find the x and y intercepts, graph our vertical asymptotes, horizontal asymptotes, and then what happens here is sometimes we need to plug in a point so that way we know where it starts, okay? And this might happen with a sine ray or anything like that. So let's check this out in the process on how to graph our rational functions, okay? All right, so here we go. We have g of x equals 1 over x plus 2. So remember, we're going to do domain first. Domain says what can't, or what makes the denominator 0, what can't it be? It can't be -2. So our domain is -infinity to -2 and -2 to infinity. Next on our list is actually to reduce it all the way. Well, guess what? It's already reduced. There's nothing we can do. So we can go on to the next one. Next thing we do is our x-intercept. Do you guys remember what we said at the beginning of this lesson? We said we set the numerator equal to 0. Well, 1 cannot equal 0, so there aren't any x-intercepts. Okay. Y-intercept. Y-intercept, remember, is when we set x equal to 0. So we would have 1 over 0 plus 2, which is 1/2. Remember to make that a coordinate pair, so it's 0, 1/2. Okay, vertical asymptotes next. So that's setting the denominator equal to 0 and solving. So if you set x plus 2 equals 0, and we solve, we get x equals -2. Horizontal asymptote, remember we look at the leading term. Well, there's only one term on top, so let's keep in mind that that is x to the 0, which means p is less than q. So if p is less than q, you automatically have a horizontal asymptote at y equals 0. Okay, so what does it mean by plug-in? Well, I will show you in a second. The first thing I'm going to do is label my y-intercept. So if that's 1, let's do 1/2. And then we have a vertical asymptote at -2. Now, the horizontal asymptote, guys, I want to show you. Vertical asymptotes, you go straight down, no big deal. Okay, but when you do horizontal, do not put your dotted line at the middle. You always, because remember, it's what's happening at the end. Okay, now, how do we know which way it goes? Does it go like a J here? Does it do an upside down J here? What happens? Well, first of all, I do know that it has to go through this point. Okay, so one thing you can do is say, hey, if this is -2, let's plug in a number. Let's plug in something on the left side of it. So -3. If I plug in -3, right? If I plug in -3, we would get -1, right? Because 1 over -1 is -1. So I know I'm down here. And what do I know with asymptotes? I get really, really close. Now, how do I know it's going down and not up? Because, guys, if it went up, I would cross the x-axis. But remember, there is no x-intercept. So it has to go down like this. And, of course, at the end here, again, because we can't cross the x axis, it gets really close to that horizontal asymptote. And on the other side, well, again, we know it's up here, right? So it can't cross this x-intercept since we have none. So I automatically know that this one is going up, and this one comes really close to the horizontal, and we're done. We just graphed a rational function without our calculator. Okay, let's do that again. We have a couple, just one more and we're done. Okay, domain. What can't x be? X cannot be -2, so our domain is -infinity to -2 and -2 to infinity. All right, now reduce it. Can we reduce anything? No, we're done. So x-intercept. Remember, x-intercept is when our numerator equals 0. So I set x plus 1 equals 0. We get x equals -1. Remember that that is a coordinate pair because it's an intercept. Now, y-intercept is when x equals 0. So when I plug in 0 for x, I get 1/2. Oops, and I almost put it as an x, right? Y-intercepts have x equals 0. Y is 1/2. Wow, this is almost turning out like our one before that, but this time we have an x-intercept. Okay. Vertical asymptote, again, we have this at x equals -2. And horizontal asymptote, we have to look at that leading coefficient, right? Or not leading coefficient, the term, sorry. So our leading term right here for both of them are x to the first. That means P equals Q. So when they equal, we take the leading coefficient in front. What's in front of that x? 1. What's in front of that x? 1. 1 over 1 is 1. So we have a horizontal asymptote at y equals 1. All right. Let's do this. X and y. Again, I'm going to graph my intercepts and my asymptotes first. Then I got to judge where it belongs. So we have a x-intercept at -1, 0. We have a y-intercept at 1/2. We have a vertical asymptote at -2. And then we have a horizontal asymptote at 1. I am not going to do this across. I'm going to do this at the end of it. Okay? At the end. All right, now we're going to have to graph. We got to figure out where this is. Well, first of all, I pretty much can assume that these two are going to cross, right? Well, what does that mean? Well, if I cross over here, knowing that this is going to be, because this is to the first, this is an odd x-intercept, right? Odd x-intercepts means we cross. So I'm going to cross. That means we're going to go down towards this asymptote. Now, of course, guys, if this is going across, we can assume that it's going towards that asymptote there. Okay? Now, what happens? Is it going to be down here, or is it going to be up here? There are little tricks that I'm not going to mention yet because I don't know if they come up earlier or later or not. So again, we're going to go back to our instructions, which then say plug in a number. So let's plug in again that -3. If I plug in -3, I would get -2 over -1, which is a +2. So at 3, I would be up here, which means I'm going to be in the upper corner, upper left. And we're done. So plugging in points really quickly helps you identify which of the 4 our graph is in. And remember to hug those asymptotes. Okay, let's practice some of those.